For introduction. Today is Professor Yao's birthday, first of all. Then this is a conference celebrating 15th anniversary of Yao Mathematical Science Center. I joined Yao Center in 2018, and actually, so this in April. So this is sixth anniversary for myself too, and I enjoyed the excellent environment for education and research. I really appreciate. So now let's start. I talk about Hodge Laplacian first, and then apply to Kuranishi family, geometric Kuranishi family of manifold, and then apply to the deformation of solitons. This is my talk. So I start with Kodaira-Spencer deformation theory, just briefly. So if H2 of tangent sheaf is 0, for example, if M is Fano, then the deformation is parameterized by the first cohomology of the tangent sheaf. The infinitesimal generator is described as the check cohomology class of the derivative of the coordinate changes. Then, so this work has history. So Cao, Sun, Yao, and Zhang studied the case when the starting manifold, Kerr-Einstein manifold. So this work was motivated by this work, and I wanted to understand some detail of this. And then, so this is try to generalize this result in some cases for Fano manifold with Xiao and Sun and Yi Zhang. And then I applied the result for Kerr-Einstein manifold, deformation Kerr-Einstein matrix to weighted solitons. So this is what I want to explain today. So I start with the Hodge Laplacian and eigenvalue. So I, as a warming up, I recall the proof of Kodaira vanishing theorem. So MG is a compact Kerr manifold, and L is a line bundle, and H is a Hermitian metric. Then the d-bar Laplacian for L-valued differential forms, 0Q forms. We have this formula. You can find this, for example, Kodaira's Moro Kodaira or Kodaira's book. So this is Laplacian part, and this is the commutator to derivative. D-bar operator is usual D-bar because we call it line bundle, and this is a connection for coming from H. And then the commutator is the curvature. So we should have a curvature of the manifold N. So G is the Kerr metric, and bundle curvature we should appear here. So this is the actual formula. From this we get Ricci curvature. Then this curvature is the curvature for L from the bundle metric H. And then so if this term is positive, by integration by parts, this minus becomes plus. So taking L to inner product eta And then if this is positive, then we get this vanishing. For if this is positive, it means minus Km anti-canonical line bundle plus L is positive for Q positive. And this is the well-known proof of Kodaira vanishing. Then we apply the same formula. Same formula for when M is a Fano manifold. Well, what is Fano manifold? The first term class is positive, so it is represented by Kähler form. So I consider this as a space of Kähler metrics. And then, so we pick a Kähler metric. I identify metric and Kähler form. So omega, I choose Kähler form, but sometimes I call metric or form. And so this Kähler form in this positive form. And then the Chern-Weig theory Ricci form also represent the first term class. So the difference is d bar of some function. And then on this F is called the Ricci potential. And then I take L to be the trivial line bundle and metric H to be this exponential F. And then we use the same formula of the Kodaira vanishing. So, sorry. So, and then, so I go back. So we apply the formula in Kodaira Moro or Kodaira with the Hermitian metric for this trivial line bundle, and then we remark that taking this metric for trivial line bundle is the same as taking the volume form of this form. The F is the Ricci potential. So it's the same thing to take the line bundle metric AEH for trivial line bundle as the taking volume form this way. And then D bar, the adjoint of D bar is the same as formal adjoint of, with respect to this L2 inner product with this weight function F. And then the formula becomes like this. So or the curvature of exponential F is minus dd bar of log of exponential F. So it's minus of F, second derivative F. But then recall that this the Ricci potential of this form. So Ricci minus metric is dd bar of second derivative F. So Ricci minus second derivative is the metric. So this becomes the metric. And this is the inverse matrix of the metric. So you take the trace, then this is the identity matrix. You take the sum over I, then it is the J beta becomes J. So J becomes J beta. So this becomes eta itself. So, but we take Q times, so we have Q times this form. So if eta is an eigen form for this Laplacian, then we have this formula. So this is positive, and Q lambda has to be bigger than or equal to Q. Also, if lambda is equal to Q, then second d bar d bar of eta is 0. It's a covariant derivative, but d bar is just a skew symmetrization of this covariant derivative. So this means d bar is also 0. This. So also eta is exact because of this vanishing. And then as a conclusion, we get this result with Sun and Jiang that if Laplacian f is the weighted Hodge Laplacian, it means the measure has weight exponential f. Then the eigenvalue is bigger than or equal to q for non-zero eigen, of course, non-zero eigen form. Then when lambda is equal to q, then it is eta is homomorphic, debug closed, sorry, debug closed. And then when eta is closed, then it must be exact. It comes from from this equation, you get this. So this is what I got. Well, this was the result I want to apply for deformations. But this is another problem. Another result we got for if d bar is not 0, then applying d bar on d bar side and d bar on the Laplacian f commutes. So therefore, then lambda has to be bigger than or equal to q plus 1, applying the previous result, and then raising the differential form for algebra tangent vectors, then this becomes a homomorphic section of this. And this is just my personal result. This is I found when I was a graduate student. When q equals to 0 case, the functions, the weighted Laplacian has eigenvalue bigger than equal to 1, and lambda equal to 1 case, this dual of gradient one form is dual of the d bar is homomorphic vector field, and this is very useful for later work for myself, but this is not what I want to apply. Well, so we want to apply this result to deformations. So now I turn to deformations. So let's recall the Kuranishi family or Kodaira-Spencer theory. So pi is a deformation, and the starting manifold I denote M0, and for the small deformation is described by this tangent vector valued 0-1 form. So this is this form. This is the infinitesimal deformation of complex structure. The small change of complex structure is described like this. Tangent vector 0-1 form, and it satisfies these three conditions. So starting point, it must be M0, so it must be 0, and this equation is just the integrability condition of the almost complex structure defined by this phi t. So it's a sort of Newland-Nielsen theorem. And then the infinitesimal deformation is satisfy this D bar vanishing, and so it defines the D bar cohomology of 0, 1 form. So this is Kodaira-Spencer, but Kuranishi described in this form using of this the first in this way. So we expand in terms T, and the first order term he used the harmonic form, but in this case we may use this twisted Laplacian, and the first order term is the harmonic form. Then this is a sort of gauge fixing condition to get a finite dimensional transverse direction. For this was considered by Kuranishi, and the first application of the Hodge Laplacian is this. This is basically due to Schaufensen's previous work. So what we want to show is that, so we started with a Kähler metric on M0, and then we consider deformations. And from rigidity of Kodaira-Spencer, MT still is a Kähler manifold, but what it's a, we tempting to know whether this original Kähler form still remains to be Kähler form of these deformations. And this is yes. This is the result of theorem D. The starting Kähler form still remains to be the Kähler form for deformations. Why? So as I said, the proof can be found in the previous work by Schaufensen for negative Einstein case, but it still applies to this positive case by using the eigenvalue estimates, because so we contract this tangent part to this 2 form, then we get 1 form of this form. So, and then from the Schaufensen's computation, we repeat, then this 2 form is a eigenform of Laplacian F with eigenvalue 1/2. 1/2. So if this is non-zero, this 2 form is non-zero, this must be bigger than or equal to 2. So this form must be 0. So this is the first observation. And then let's let's see what happens for this omega. The omega remains to be closed form. It's just a differential. This holds for any for a given differentiable manifold, even complex structure changes. So and then omega remains to be a Kähler form if this Kähler form is JT invariant. But then this we can show by computation that omega is JT invariant if and only if this form is 0. So this also go back to Schaufensen's earlier work. So I just omit the I do not have to, I will not want to explain this part. But so anyway, from the eigenvalue estimate combined with this equation, omega phi is 0, phi omega is 0. So this is JT invariant. Combining this, omega is still a Kähler form. So we get theorem D, and then we want to know what is the Ricci potential. So Ricci potential is the difference between Ricci form and Kähler form. So we know that this omega is still a Kähler form for this deformed MT. And the answer is that the Ricci form is given by this equation. So T, so we have to d bar, but we have to take the deformed dt and d bar T operator, and the phi appears here for the deformation from the Kuranishi family. This is the second result of with Sun and Zhang. And so this case, this is actually essentially proved my Ian Zhang's thesis. Just modified this when Ricci is not Einstein. So for general Fano manifold, we have Ricci potential F. So combining this F, this can be Ricci potential F. So combining this F, this can be written in this way. So and then I said I go back to this previous works. So so they study the deformation of Kähler Einstein manifold and the Kuranishi family, and they gave a necessary and sufficient condition for this Kähler metric to extend nearby deformations. Then next I want to discuss about the Ricci solitons or its generalization Ricci soliton. This is recently studied by people like this notion appeared from different contexts, like a conformally Kähler Einstein matrix or its extensions. And then, so I'll do it now. So what I want to say that so this result for Kähler Einstein matrix can be extended to weighted solitons. Weighted solitons include Ricci solitons, Kähler Ricci solitons. So what is weighted solitons? So this. So what I said, well, this comment I explained in detail. So now I turn to weighted solitons on Fano manifolds. So M is a Fano manifold, and first term class positive, so it considers Kähler class. And then Kähler form is just this way. I already used this. And then let T be a toral subgroup of automorphisms of M, and assume omega is T invariant. And then Fano manifold is simply connected, and then torus action is always Hamiltonian with respect to omega. And we have a canonically normalized moment map. Canonically, what this means? So if symplectic form is the first term class of a line bundle, the simple moment map can be uniquely normalized by lifting to a line bundle. And then, so in this case, anti-canonical line bundle is the it has the function class omega C1. So anti-canonical lemon, there's a natural torus action. So it gives a canonical normalization. It is related to the Laplacian eigenfunction, eigenvalue related, but I will not go into detail. But anyway, this general theory, it has a unique normalized moment map. Then I shouldn't. I don't want to say more much about it. But let's delta to be the moment map image, which is a moment polytope. And then this delta is independent choice of omega. Why is this? Because the vertices of the moment polytope corresponds to critical point of the moment map. Moment map satisfies some in the critical point do not change when symplectic form belongs to the stay in the same cohomology class. It's sort of general fact. So and then V be a positive function. Let V be a positive function of delta. Then using action angle coordinates, we regard V as a function of mu. Mu is the moment map, but mu can be used the coordinates on the moment map image. So in that case, I write V mu, but we can pull back this function by this moment map. Then this becomes smooth function of M. And then we write mu sub omega, which means pull back of V by the moment map. So it's a composition of mu. So I somewhat complicated, but I said this because I want to, sorry. I want to explain this. I want to define this V soliton. So suppose, so we say a Kähler metric is a V soliton, weighted V soliton, or simply V soliton if Ricci minus omega is d bar of log of V mu omega. So V is a function on the moment map image. Moment map image is invariant under the change of Kähler class in the fixed Kähler class. So, and then pull back mu by V by mu, then this becomes a function on M. So we can take log and d bar. When it happens that this equation is satisfied, we say omega is a weighted V soliton. So Ricci form is, of course, the usual formula given by usual formula. So, and then we sometimes say V soliton or just we weighted soliton or V soliton. V soliton is too long. So, and then, so the example, this is a rather new notion in differential geometry, but it contains many nice examples. For example, if when V is a exponential of mu z. What is this? Z is a fixed element in rearrangeable torus. And mu, so this is z is fixed and mu is a variable on the image of the moment map. So this is a linear function with a coefficient z and mu variable. Then exponential x f can be considered a function on the moment map image. In this case, the V soliton is the Kerr-Rich soliton. And Kerr-Rich soliton is necessarily of this form. And then if you take V to be the linear function plus A for some positive function A, then the weighted soliton is something called Mabuchi soliton. Mabuchi soliton is like so Ricci minus omega is we write d above f, and when f is a hormone killing potential, it is Kerr-Rich soliton. This case, exponential of f is a hormone killing potential. And Mabuchi studied this as an analog of this Kerr-Rich soliton and has many similar properties. And then another unexpected example is this one. So I added some positive A because I assumed V is positive. So that I add positive constant A. Again, this I add some positive A so that this becomes positive, and then minus M minus 2. M is a complex dimension M. Induces Sasaki-Einstein metric on the U1 bundle of the canonical line band. This is somewhat unexpected example of weighted V soliton. So, so this our theory include all of this as a special case, and then we try to extend. I have to finish. What time did I start? I have to finish now. Sorry. So we apply the same proof as done in Sun, Cao, Sun, Yao, and Zhang. We get the same result. So starting point is so the following equivalent. The starting M0 has a weighted V soliton, then nearby MT still have weighted soliton if and only if dimension of the T equivalent automorphism group do not change the dimension. But this is also equivalent to T equivalent automorphism of isomorphic. Sorry,
Or comments? So may I ask you a question? So you also studied about the existence of K-Einstein under deformation, right? So under what conditions the Fano condition can be relaxed? So you needed to assume Fano manifold, right?
Yeah, Fano manifold, yes.
So can this Fano condition be relaxed?
Relax. Should be difficult, but might be possible. I don't know.
Okay,
so,
thank you.
Yeah.
Okay, thank you.
CSCK or yeah.
Okay, thank you,
Yeah.
thank you.
The notion can be extended. So problem can still
I see.
be extended.
Okay, so we thank the speaker again, and the next talk is by Professor Hosono.